Look up at the night sky on a clear evening, and you might catch a glimpse of Jupiter, a brilliant, steady beacon among the twinkling stars. But what you see from Earth is only a hint of the majesty and mystery waiting out there. Imagine a world so vast that all the other planets in our solar system could fit inside it with room to spare. A place of endless, turbulent storms, strange auroras dancing at its poles, and a deep, hidden interior that may hold secrets about the very origins of our solar system. This is Jupiter, not just a planet, but a realm of wonders that has captivated astronomers, scientists, and dreamers for centuries. Yet for all we've learned, Jupiter remains one of the most enigmatic places we've ever observed. Every answer seems to raise new questions. Why does it have a giant, centuries-old storm big enough to swallow Earth whole? What creates its stunning, complex cloud bands, shifting and swirling in hypnotic patterns? How does a planet with no solid surface generate a magnetic field so powerful it dwarfs our own? These aren't just scientific curiosities, they're clues to understanding not only Jupiter itself, but the story of how planets form, how solar systems evolve, and perhaps even how life might emerge in the most unexpected places. And that's just the beginning. In this video, we're setting off on a journey to explore 25 of the most baffling, intriguing, and utterly mesmerizing mysteries of Jupiter. From its mysterious core to its faint, dusty rings, from its family of diverse moons to its immense, invisible influence on the solar system, each mystery pulls us deeper into the awe and wonder of this gas giant. So join us as we dive into the questions that continue to challenge our brightest minds and remind us that the universe is far stranger and far more magnificent than we often dare to imagine. For centuries, astronomers imagined Jupiter with a dense, solid heart, a rocky or metallic core that acted as the foundation for the entire planet. It seemed like a fundamental truth, the obvious starting point from which such a colossal world would have begun to form. But when NASA's Juno spacecraft arrived at Jupiter in 2016, it began sending back data that turned this very idea on its head. The measurements of Jupiter's gravity field were unlike anything scientists had predicted. Instead of pointing toward a compact, well-defined center, the data suggested something far stranger, something that forces us to rewrite the textbooks on how giant planets are born. What Juno found hints at a core that isn't solid at all, but rather a vast, diluted, and partially dissolved region that might blend gradually into the swirling ocean of metallic hydrogen above it. Think of it not as a distinct rocky marble at the center, but more like a thick, murky soup where heavy elements, rocks, minerals, perhaps even diamonds, are mixed and dissolved into the fluid interior, stretching across nearly half of Jupiter's radius. This fuzzy or diluted core presents a monumental puzzle. If a giant planet doesn't form around a solid anchor, how does it even begin to come together? This mystery strikes at the very heart of planetary formation. The leading theory, called core accretion, suggests that first, a solid core forms from the dust and ice of the early solar system. Once this core becomes massive enough, perhaps 10 to 20 times the mass of Earth, its gravity becomes strong enough to rapidly pull in enormous amounts of hydrogen and helium gas from the surrounding nebula, snowballing into a gas giant. But Jupiter's apparent lack of a traditional, compact core throws a wrench into this elegant model. Did it once have a solid core that was somehow obliterated by the intense heat and pressure over billions of years, its material stirred and diluted into the surrounding soup? Or did it form through a different process entirely, perhaps a gravitational collapse in the disk of material around the young sun that skipped the step of building a large core first? Each possibility leads us down a different path in understanding not just Jupiter, but every gas giant we've discovered orbiting distant stars. Now, let's turn from the hidden depths of Jupiter's core to a tempest so vast it's visible from Earth with even a small telescope, the Great Red Spot. This colossal, swirling storm is arguably the most famous feature in our entire solar system, a raging anticyclone large enough to engulf our entire planet. But its most baffling characteristic isn't its size or its striking brick red color. It's its impossible longevity. Hurricanes on Earth are measured in days or at most a few weeks before they dissipate, their energy stolen by friction with the land or cool ocean waters. Yet the Great Red Spot has been churning in Jupiter's southern hemisphere for at least 400 years and possibly much longer. What cosmic engine could possibly power a storm for centuries, and why is it showing signs of finally, after all this time, beginning to fade? To understand its endurance, we first have to understand what it is. The Great Red Spot is a high-pressure storm, an anticyclone, meaning it rotates counterclockwise in Jupiter's southern hemisphere. It's essentially a massive, stable atmospheric feature, trapped between two powerful jet streams that flow in opposite directions, effectively pinning it in place. Unlike on Earth, there's no solid ground beneath it to disrupt its circulation. It spins within Jupiter's deep atmosphere, a fluid environment that provides a near-endless source of energy. The storm acts like a giant wheel, drawing up warmer material from deep below and releasing cooler gases from above, a continuous cycle that has helped sustain its fury across generations of human observation. But the mechanics run even deeper. Scientists believe the storm's incredible longevity is tied to its ability to absorb smaller vortices, other storms that form constantly in Jupiter's turbulent atmosphere. It acts as a dominant predator in the meteorological food chain, consuming these smaller systems and stealing their energy to maintain its own strength. Furthermore, it's thought that the storm might extend roots deep into the planet's interior, possibly tapping into internal heat rising from below to fuel itself. This internal heat, left over from Jupiter's formation and released through gradual gravitational compression, is the true key. It creates the immense temperature gradients and powerful convection currents that drive the entire Jovian weather machine, providing a constant energy source that our planet, which receives most of its weather-driving energy from the external sun, simply doesn't possess. Yet, for all its historic resilience, the Great Red Spot is changing. Continuous observations since the 1800s show the storm has been steadily shrinking. What was once measured at over 25,000 miles wide, large enough to fit 3 Earths side by side, is now a fraction of that size. Recent data suggests it's not just getting smaller, it's also becoming more circular rather than oval, and its iconic reddish hue has been deepening and intensifying. Some researchers propose the shrinkage and color change could be related. As the storm contracts, it may be concentrating the mysterious chemicals that give it its color, or the increased intensity of its winds could be dredging up different compounds from deeper atmospheric layers. The most pressing question now is whether this is a natural, cyclical process where the storm will eventually rejuvenate, or if we are witnessing the slow, final act of a solar system legend. Its potential disappearance would rob us of a celestial icon, but studying its demise could finally unlock the secrets of its incredible, centuries-long life. While the Great Red Spot dominates Jupiter's visual landscape, an even more immense and powerful feature remains completely invisible to our eyes. This is the planet's magnetosphere, a teardrop-shaped bubble of magnetic influence so colossal it could contain the sun without touching the sides. If you could see it in the night sky from Earth, it would appear larger than our own moon. At the heart of this invisible shield lies the engine that creates it, Jupiter's magnetic field, a force 20,000 times more powerful than the one that protects our planet. But its sheer strength is only the beginning of the mystery. Unlike Earth's relatively orderly field, which emerges from a spinning core of molten iron and roughly aligns with our planet's rotational axis, Jupiter's magnetic field is a chaotic and lopsided masterpiece. The source of this incredible power is believed to be a vast, spinning ocean deep within the planet. At the tremendous pressures found in Jupiter's interior, the hydrogen that makes up most of its bulk undergoes a bizarre transformation. It ceases to behave like a gas and instead becomes a liquid metal. This sea of metallic hydrogen, swirling at incredible speeds as the planet rotates once every 10 hours, acts as a phenomenal electrical conductor. It's this churning, supercharged fluid that generates the magnetic field through a process called a dynamo, much like the dynamo inside Earth, but on an almost unimaginable scale. However, the Juno spacecraft's detailed maps revealed that Jupiter's field is far more complex and irregular than any model predicted. It's not a simple, symmetrical bar magnet shape. It's a tangled mess of intense and weak spots, with an astonishingly strong region in the northern hemisphere that scientists have nicknamed the Great Blue Spot. This feature isn't blue in color, but the name distinguishes it from the Great Red Spot and denotes its presence in magnetic field maps. It's an intense, localized patch of magnetic flux where the field lines are extraordinarily concentrated. The most baffling aspect of this Great Blue Spot is its location. It doesn't align with Jupiter's North Pole or its rotational axis. This misalignment suggests that the dynamo generating the field is not operating uniformly throughout the metallic hydrogen layer. Instead, it points to a process that is much more turbulent and patchy, possibly originating from different depths or being influenced by the planet's mysterious, diluted core. Some scientists theorize that the immense pressure at Jupiter's center might even be forcing hydrogen into an even more exotic state, perhaps solid metallic hydrogen, which could be playing a role in distorting the magnetic field. The irregularity of the field has profound consequences. It means the auroras at Jupiter's poles, the most powerful in the solar system, are not neatly contained rings like our northern lights. They are sprawling, unpredictable, and immensely energetic displays, fueled not only by the solar wind, but also by material being flung from Jupiter's volcanic moon, Io. Furthermore, the lopsided nature of the magnetic field means that radiation levels around the planet are not evenly distributed, creating zones of extreme danger for any future spacecraft. This magnetic chaos forces us to reconsider our fundamental understanding of how dynamos work inside fluid planets. Jupiter presents a natural laboratory of extreme physics, showing us that under enough pressure and rotation, magnetic fields can behave in ways we are only beginning to comprehend. But the bizarre behavior of Jupiter's magnetic field is only half the story. Its true spectacle is revealed in the planet's polar regions, where the most powerful light show in the solar system defies all our expectations. These are the Jovian auroras, vast curtains of shimmering energy that can be hundreds of times brighter than the auroras we see on Earth. Yet their immense power is just the first layer of a profound mystery, because the forces that create them and the strange rhythms they follow are unlike anything found on our own world. On Earth, our beautiful northern and southern lights are almost entirely a gift from the sun, sparked when charged particles from the solar wind are funneled by our planet's magnetic field down into the upper atmosphere, where they collide with gas molecules and release energy in the form of light. Jupiter, however, operates on a completely different principle. While the solar wind does play a minor role, the primary engine behind Jupiter's colossal auroras is the planet itself, along with its volcanic moon, Io. Io spews vast amounts of sulfur and oxygen ions out into space, creating a giant, donut-shaped cloud of plasma that gets caught in Jupiter's ferocious magnetic grip. As the planet rotates at breakneck speed, it drags this heavy cloud of ions along with it, generating immense electrical currents that flow directly into the polar atmospheres. It's this internal, self-sustaining mechanism, a planet essentially creating its own stunning light show from material supplied by its moon, that generates such unbelievable and continuous power. The real puzzle, however, involves a form of light our eyes cannot see. Jupiter's auroras produce tremendous, pulsing flares of X-ray radiation, an extremely high-energy light typically associated with the most violent objects in the universe, like black holes and neutron stars. For a planet to be a significant source of X-rays is astonishing in itself, but the behavior of these X-ray pulses is what truly confounds scientists. At the North Pole, these X-ray auroras have been observed to flare with an incredibly precise rhythm, erupting like a cosmic lighthouse every 27 minutes. This clockwork regularity suggests a highly organized, repeating process is at work, a stark contrast to the chaotic and turbulent atmosphere we see everywhere else on the giant planet. The leading theory suggests these X-ray pulses are tied to vibrations within Jupiter's magnetic field lines. Imagine plucking a giant, invisible violin string that stretches millions of miles through space, connecting Io's plasma cloud to Jupiter's pole. As the heavy plasma from Io moves along these magnetic field lines, it may be causing them to vibrate or generate waves. These waves then travel along the field lines at incredible speeds, eventually crashing into the planet's atmosphere and compressing it, which heats the ions and causes them to emit X-rays in a regular, repeating burst. It's a captivating idea that the entire magnetosphere might be resonating like a giant musical instrument, but it remains unproven. Unraveling this mystery is crucial because it doesn't just apply to Jupiter. It offers a new window into how planetary magnetic fields interact with their environments across the cosmos, and how energy can be transferred across vast distances of space in the most unexpected and beautiful ways. This journey from the planet's shimmering poles into the very engine of its being brings us to one of the most fundamental mysteries of all. Where does Jupiter get all its energy? Every parent knows that if you leave the refrigerator door open, the kitchen gets warmer, not colder. In a similar way, a planet like Earth, warmed primarily by the sun, reaches a certain equilibrium. It radiates back into space almost exactly the same amount of heat energy that it absorbs from sunlight. Jupiter, however, breaks this simple balance in a spectacular fashion. Measurements show that the giant planet is radiating out nearly twice as much heat as it receives from the distant sun. This means Jupiter has a powerful internal heater, a vast reservoir of energy bubbling up from within its own deep interior to warm its cloud tops and fuel its violent storms. The question of what exactly is stoking this furnace has been a central puzzle since it was first discovered. One of the leading explanations is a process called the Kelvin-Helmholtz mechanism, a relic of the planet's very formation. Think of it like this: Jupiter is a massive ball of gas, primarily hydrogen and helium, and it is still slowly, imperceptibly shrinking under its own immense weight. As gravity pulls this enormous mass inward, the compression converts gravitational energy into thermal energy, heating the interior. It's a principle you can feel on a small scale when you use a bicycle pump. The air inside gets hot as you compress it. For Jupiter, this process has been ongoing for 4.5 billion years, providing a steady, long-term source of internal warmth. This primordial heat is the leftover energy from the planet's violent birth, and it's slowly leaking out into space, accounting for a significant portion of that unexplained temperature anomaly. But some scientists wonder if primordial heat from contraction alone is sufficient to explain the total energy budget, especially when we consider the planet's immense size and age. This has led to more exotic and far more controversial theories. One captivating idea proposes that deep within Jupiter's core, where pressures are millions of times greater than Earth's atmosphere and temperatures soar to tens of thousands of degrees, a form of nuclear fusion might be occurring. Not the violent hydrogen fusion that powers our sun, but something far more subtle. This theory suggests that under such extreme conditions, a form of pycnonuclear fusion, a reaction driven by incredible density rather than high temperature, could be taking place among metallic hydrogen or other light elements. In this scenario, the planet's own heart could be generating a tiny, smoldering nuclear flame, contributing to its internal heat. Another, perhaps even more speculative, hypothesis involves a rain of diamonds. In Jupiter's deep atmosphere, the tremendous pressure is thought to squeeze methane gas into soot, which then hardens into graphite and is compressed further into actual diamond. Scientists theorize that vast hailstorms of these diamonds could be falling through the planet's interior. As they sink into even hotter and denser regions, these diamond icebergs might eventually melt into a liquid carbon sea. This process of precipitation and melting would release gravitational energy, effectively acting as a slow, continuous internal engine, converting the potential energy of falling diamonds into additional heat. While these theories are not yet part of the mainstream, they highlight just how strange the physics inside Jupiter can get, and how a simple heat imbalance can push our imaginations to the very limits of known science. The true answer likely lies in a combination of these processes, a symphony of gravitational, chemical, and perhaps even nuclear forces working in concert to keep this ancient giant warm. From the planet's warm heart to its dynamic atmosphere, we now arrive at one of Jupiter's most visually stunning and perplexing features, its bands. Glance at any detailed image of the gas giant, and you're immediately struck by its appearance, a world meticulously striped in shades of cream, ochre, orange, and brown. These are not random swirls, they are structured, organized, and persistent bands known as zones and belts that wrap the entire planet in a beautiful but baffling meteorological tapestry. The lighter-colored bands are called zones, where the atmosphere is rising, and the darker ones are belts, where it is sinking. But this orderly description only scratches the surface of a system that is profoundly chaotic, asymmetrical, and defies our basic expectations of how a spinning, fluid world should behave. The first mystery lies in their motion. These bands are not static decorations, they are powerful jet streams, raging rivers of wind in the upper atmosphere. And here's where the true strangeness begins. The bands immediately adjacent to each other blow in opposite directions, some eastward, some westward, at speeds that can exceed 350 miles per hour. On Earth, our jet streams are largely driven by temperature differences between the poles and the equator and are disrupted by the presence of continents. Jupiter has no land, no solid surface to create friction or disrupt the flow. It is a pure fluid dynamics laboratory on a planetary scale. Yet, despite this perfect, unbroken environment, the banded structure remains incredibly stable over long periods, even as the individual jet streams within them rage against each other. What prevents these opposing, high-speed winds from simply shearing each other apart and dissolving into a featureless haze? The energy required to maintain this stable turbulence is immense, and its source remains one of the great unanswered questions in planetary science. Diving deeper, we find that the asymmetry between the northern and southern hemispheres adds another layer of intrigue. The jet streams are not arranged in a perfectly symmetrical mirror image across the equator. Their number, their width, and even their power differ from north to south. This asymmetry points to something fundamental happening deep beneath the visible cloud tops. It suggests that the processes driving this system are not uniform throughout the planet's interior. Some scientists theorize that the strange, diluted core we discussed earlier could be playing a role, its lopsided structure and interaction with the metallic hydrogen layer influencing the circulation patterns that eventually manifest as these chaotic bands far above. It's a reminder that what we see on the surface is just the ghostly echo of violent and complex activity occurring hundreds or even thousands of miles below. Perhaps the most visually obvious mystery is the color of these bands. Why are some white and others a deep reddish brown? The prevailing theory is that the zones, being regions of upwelling, are where ammonia ice crystals are carried high into the upper atmosphere, forming bright white clouds that reflect sunlight. The belts, conversely, are areas of sinking air, As the atmosphere descends, it clears these high, white clouds, allowing us to see deeper into the atmosphere where more exotic compounds reside. The leading candidates for the darker colors are compounds containing phosphorus or sulfur, or complex hydrocarbons known as tholins, which are created when simple gases like methane and ammonia are exposed to ultraviolet light from the sun. It's a form of planetary sunburn, a photochemical reaction that creates a reddish slurry, but the colors are not constant. They change, sometimes dramatically, over years or decades. A dark belt can suddenly lighten, or a white zone can deepen into a rich ochre for reasons we do not fully understand. This suggests that the chemical soup responsible for the coloring is not evenly distributed or is being affected by deeper, internal processes we cannot directly observe. Major upheavals, like a sudden and complete fading of the entire south equatorial belt, which has happened several times in recorded history, hint at planet-wide climate cycles we are only beginning to detect. Jupiter's stripes are not a static painting. They are a dynamic, living weather map, and we are still learning the language it uses to tell its story. Yet the most fundamental questions about a planet often begin with its most basic ingredient, water. When the Galileo probe plunged into a seemingly dry and cloudless patch of Jupiter's atmosphere in 1995, its measurements sent a shockwave through the planetary science community. It found that the abundance of water, along with oxygen, was far lower than anyone had predicted. For decades, scientists had assumed that Jupiter, forming in the cold outer solar system beyond the frost line where water ice is stable, would have been a water-rich world. It should have acted as a giant sponge, soaking up water ice from the protoplanetary disk as it grew. The Galileo data suggested a puzzlingly dry world, but because it sampled only one single anomalous location, the hope remained that it had simply plunged into an unexpected desert. This hope placed a heavy burden on the Juno mission, which arrived with more advanced tools to conduct a global survey. Using its microwave radiometer, Juno had the unique ability to peer deep below the visible cloud tops, probing tens to hundreds of kilometers into the atmosphere to measure the water abundance at different depths and latitudes. The results were not just surprising, they were deeply perplexing. Juno discovered that the water abundance is not uniform across the planet. The equatorial region, in particular, appears to be surprisingly dry, containing only about 0.025% water by molecule at the cloud-forming level. That's several times less than the Sun's measured abundance of oxygen, and a fraction of what theory suggested a gas giant should hold. This elusive water mystery strikes at the very model of how our solar system came to be. If Jupiter, the first and largest planet to form, is unexpectedly dry, it forces us to reconsider the entire environment of the early protoplanetary disk. Was the region where Jupiter was born somehow deficient in water ice, contrary to all our models? Or did Jupiter's formation process itself somehow lock away or expel a vast amount of its water? One compelling theory suggests that Jupiter might have formed first from a region of the disk that was too warm for water ice to condense efficiently, only later migrating to its current position and accreting drier material. Another, more dramatic idea is that a young, hot Jupiter might have experienced a colossal impact with a planetary-sized embryo early in its history, a collision so violent that it blasted a huge portion of the planet's volatile, rich outer layers away into space, leaving behind a comparatively dehydrated core. The water is somewhere, it's just not where or in the amount we expected to find it. Solving this puzzle is about more than just accounting for missing molecules. It's about accurately reading the recipe book that nature used to build our entire planetary neighborhood. When we think of ring systems in our solar system, Saturn's magnificent ice and rock jewelry immediately comes to mind. But Jupiter, too, possesses a set of rings, though they are so faint and ethereal that they remained completely hidden from view until the Voyager 1 spacecraft looked back toward a crescent Jupiter in 1979 and captured them silhouetted against the blackness of space. Unlike Saturn's brilliant bands, Jupiter's rings are tenuous and dusty, a ghostly halo that seems almost out of place around such a massive and boisterous planet. Their very existence presents a quiet enigma, but their specific, bizarre structure transforms that puzzle into a full-blown cosmic mystery. The first and perhaps greatest surprise is what these rings are made of. While Saturn's rings are composed largely of water ice, creating highly reflective surfaces that shine brilliantly in the sunlight, Jupiter's rings are incredibly dark. They absorb almost all the light that hits them, reflecting a mere 5% or less. This tells us they are not made of clean ice, but of very fine, dark dust particles no larger than the specks you might find in a smoky room. This dust doesn't originate from some primordial disk of material left over from the planet's formation. Instead, it's constantly being remade and replenished in a violent, ongoing cycle. The primary source is believed to be microscopic debris knocked off the surfaces of Jupiter's small inner moons Metis, Adrastea, Amalthea, and Thebe by the relentless barrage of micrometeoroid impact. These tiny moons, orbiting within and near the rings, act like celestial quarries, supplying a continuous stream of fresh dust to replace the particles that slowly spiral inward toward the planet's atmosphere. This process of destruction and renewal explains the rings' existence, but it doesn't explain their truly bizarre and unexpected shape. From our understanding of orbital mechanics, we would expect a ring system to be almost perfectly flat, a razor-thin disk aligned with the planet's equator. Gravity should pull every particle into this single, stable plane, but Jupiter's rings defiantly break this rule. The main ring, and particularly a structure known as the halo ring that lies closer to the planet, exhibits significant vertical thickness. In some areas, this halo extends thousands of kilometers above and below the equatorial plane, creating a torus or donut-like shape that bulges out around the planet. How can such tiny, non-interacting dust particles defy gravity and maintain this puffed-up structure? The answer appears to lie in electromagnetic forces acting on the dust itself. The particles constantly blasted off the moons are not neutral. They become electrically charged either by interacting with solar ultraviolet light or by colliding with the intense plasma trapped in Jupiter's powerful magnetic field. Once charged, these microscopic specks are no longer solely under the sway of gravity. They become subject to the planet's overwhelming magnetic forces. Jupiter's magnetic field is tilted relative to its rotation axis, and it also wobbles or precesses over time. Theorists propose that this dynamic, wobbling magnetic field interacts with the charged dust grains, pushing and pulling them, forcing them to oscillate above and below the equatorial plane. It's this electromagnetic interaction, a constant tug of war between gravity and magnetism, that is thought to pump energy into the particles' orbits, preventing them from settling into a flat disk and instead creating that mysterious, voluminous halo. We are essentially looking at a ring system sculpted not just by gravity, but by invisible magnetic hands. Even more peculiar are the transient clumps and delicate spiral patterns that spacecraft have detected within the Gossamer rings extending from the moons Amalthea and Thebe. These faint outer rings show subtle, arc-like brightenings and what appear to be radial, spoke-like features, similar to but much fainter than those seen in Saturn's rings. The mechanisms for creating these patterns are still poorly understood, but they likely involve complex gravitational resonances with the moons themselves or even the shadow Jupiter casts into space. As the planet orbits the Sun, its shadow moves across the ring system, and the dramatic change in temperature and electrical charging as dust particles move from sunlight into shadow and back again could cause them to shift and clump in ways we are only beginning to model. Jupiter's rings, therefore, are far from a static museum piece. They are a dynamic, ever-changing environment, a delicate dance of destruction and creation, of gravity and magnetism, playing out on a scale that is both humbling and profoundly beautiful. If you could hear Jupiter, it would not be the gentle whisper of solar wind or the faint crackle of distant lightning. Instead, you would be met with a deafening, otherworldly roar, a chaotic symphony of radio noise so powerful it can be picked up by ham radio operators and university antennas right here on Earth. This isn't a constant, steady signal. It's a tempest of static that erupts with unpredictable fury, a phenomenon so intense that for decades after its discovery in the 1950s, astronomers half-jokingly nicknamed it the radio emissions from hell. The source of this infernal racket is not the planet alone, but a spectacular and complex gravitational dance between Jupiter and its tortured moon, Io, a partnership that creates the single most powerful natural radio source in our entire solar system. The engine of this incredible phenomenon is a fundamental process of electromagnetism. Anytime a charged particle is accelerated, sped up, slowed down, or forced to change direction, it emits radiation. On Jupiter, the key players are electrons, and they are being accelerated on a truly monstrous scale. This fantastic acceleration is made possible by a colossal electrical circuit, one that stretches over 900,000 miles through space, directly linking the volcanic surface of Io to the cloud tops of Jupiter. Io is the most volcanically active body in the solar system, constantly spewing vast amounts of sulfur dioxide gas and other materials into its thin atmosphere. This constant outgassing creates a donut-shaped cloud of plasma, a superheated soup of ions and electrons that traces Io's orbit around Jupiter. This feature is known as the Io plasma torus. As Jupiter's incredibly powerful magnetic field spins past the relatively slow-moving Io and its torus, it treats this cloud of charged particles like a generator. The magnetic field lines, rigidly attached to the rapidly spinning planet, sweep through the plasma torus and in doing so, induce a potential difference of a staggering 400,000 volts. This generates an enormous electric current, estimated at 1,000,000 amperes, that flows along Jupiter's magnetic field lines. This current, aptly named the Io flux tube, acts like a gigantic, invisible extension cord, plugging the moon directly into the planet's polar regions. The electrons within this current are the ones being violently accelerated, and as they are forced to spiral along the magnetic field lines toward Jupiter's poles, they emit their energy not as visible light, but as intense bursts of decametric radio waves, the signature scream we detect across interplanetary space. The reason these emissions seemed so hellish and unpredictable to early observers is that they are tightly beamed, like a spinning lighthouse beacon, and their visibility from Earth is exquisitely dependent on the orbital position of Io. The radio beams are not emitted in all directions. They are concentrated into narrow cones that are tipped at an angle relative to Jupiter's magnetic axis. For listeners on Earth, we can only hear the radio roar when this invisible lighthouse beam sweeps across our planet during Jupiter's 10-hour rotation, and crucially, only when Io is in just the right position in its orbit to be actively powering the generator. It's a celestial alignment that must be precisely right for the signal to be received, making the emissions appear to come and go with a chaotic rhythm that long baffled scientists. Studying this phenomenon is about far more than just understanding a cosmic noisemaker. The Io-Jupiter interaction is one of the most direct and dramatic examples of a star-planet or planet-moon electrodynamic coupling we can observe. It provides a natural laboratory for studying how energy and matter can be transferred across vast distances in space through magnetic connections, a process that is likely fundamental to the behavior of exoplanets orbiting distant stars, particularly those with strong magnetic fields. Furthermore, this intense radiation is a major component of the lethal radiation belts that surround Jupiter, presenting a formidable challenge for spacecraft navigation and teaching us about the extreme environments that can exist within planetary systems. This radio roar from Jupiter is a testament to the fact that even in the vacuum of space, connections are everywhere, forged not by physical contact, but by the invisible, powerful lines of magnetic force. If you've ever been caught in a thunderstorm on Earth, you know the raw power of nature, the brilliant flash of lightning followed by a booming crack of thunder. For centuries, we assumed that lightning across the cosmos would follow the same basic rules we observe here. But Jupiter, as it so often does, had a surprise in store. When the Voyager probes first detected radio signals indicative of lightning in the Jovian atmosphere, it seemed to confirm a familiar process. However, decades later, with the sharper eyes of the Juno spacecraft, we discovered that Jupiter's lightning is not just more powerful than Earth's. It operates on a completely different set of physical principles, creating storms that defy everything we thought we knew about planetary weather. The first major shock came from Juno's navigation camera, which was designed to track stars but instead captured thousands of brilliant flashes illuminating the deep Jovian cloud tops. These weren't just random strikes, they were concentrated near the poles, a direct inversion of the pattern on Earth, where lightning is most common in the tropical regions. This polar preference was the first clue that Jupiter's electrical engine is driven by a fundamentally different heat source. On our planet, the sun heats the equator most intensely, driving the powerful convection that spawns thunderstorms. Jupiter, however, relies on its own internal warmth, which rises relatively uniformly. But at the poles, where the upper atmosphere is less stirred by the planet's ferocious jet streams and potentially more unstable, this internal heat can create the perfect conditions for massive storm systems to brew and generate lightning. The real mystery, however, lay not in whether lightning was happening, but how it was forming. Juno's microwave radiometer revealed something even more bizarre: a population of shallow lightning, flashes originating incredibly high up in the atmosphere, at altitudes where the temperature is a frigid -100 degrees Fahrenheit. According to every terrestrial model, this is simply impossible. On Earth, lightning requires slushy water clouds. The process begins when upward-moving air currents, updrafts, cause collisions between supercooled water droplets and small ice crystals. These collisions separate electrical charge, with lighter, positively charged ice crystals being carried to the top of the cloud and heavier, negatively charged graupel, soft hail falling to the bottom. This separation builds up a massive voltage differential until the atmosphere can no longer resist it, discharging in a brilliant flash of lightning. But at the cold, high altitudes where Juno found these shallow flashes, pure water simply cannot exist in a liquid or slushy state. It would be frozen solid. So what substance is playing the role of water in this alien meteorological drama? The answer appears to be ammonia. Scientists propose that at these heights, ammonia acts as an antifreeze, mixing with water to create an ammonia-water slurry that can remain liquid at much lower temperatures. It's within these exotic, frigid clouds that the charge separation is somehow occurring, creating lightning in an environment we once believed was utterly inert. This discovery alone rewrites the textbook on how lightning can form on other worlds. And the strange role of ammonia doesn't stop there. This shallow lightning is intimately tied to another, even more whimsical-sounding but crucial phenomenon: mushballs. These are not your average hailstones. On Jupiter, a hailstone begins its life much like on Earth, with a tiny nucleus around which ice accumulates. But in the Jovian atmosphere, that ice is an ammonia-water cocktail. As the hailstone falls, it encounters ever thicker layers of atmosphere and grows to an immense size, potentially reaching widths of a foot or more. Crucially, because of the ammonia antifreeze, these giant hailstones don't solidify into hard ice. They remain a slushy, semi-liquid mass, a mushy ball falling from the sky. These mushballs are far more than a meteorological curiosity. They are a key piece of a planet-wide puzzle. For years, astronomers had noticed that ammonia was curiously depleted in parts of Jupiter's upper atmosphere, seemingly sucked down into the deeper layers. The mushball theory provides the missing mechanism. These massive, slushy hailstones become vehicles, effectively shuttling ammonia from the upper atmosphere where the shallow lightning forms all the way down into the planet's deep interior. They fall until they reach a level where the temperature is so high that they completely evaporate, releasing their ammonia cargo into a hidden reservoir far below the visible cloud decks. This process of mushball precipitation creates a complete cycle that explains the mysterious distribution of ammonia and the very existence of lightning in places it should not be able to form. What we are witnessing on Jupiter is a completely alien form of weather, a water-ammonia cycle that parallels but is utterly distinct from Earth's water cycle. It's a system where antifreeze clouds spawn high-altitude lightning and slushy icebergs rain down to bury ingredients deep within the planet. This isn't just a minor variation, it's a revelation that forces us to broaden our understanding of atmospheric physics. The conditions that create weather are not universal. By studying Jupiter's unexpected lightning, we are essentially learning a new language of meteorology, one that will undoubtedly help us interpret the wild and exotic weather patterns on the countless giant planets we are discovering orbiting other stars. Moving inward from the faint whisper of its rings, we arrive at Jupiter's magnificent family of moons, a miniature solar system in its own right. At the center of this family are the four legendary Galilean moons, Io, Europa, Ganymede, and Callisto, each a world of profound mystery and wonder. But beyond these four giants, Jupiter's gravitational influence holds sway over a vast collection of smaller captured asteroids and moonlets, over 90 in total. This distribution of moons, from a handful of massive worlds to a cloud of tiny fragments, seems to make intuitive sense. However, this arrangement hides a glaring and puzzling gap that has forced planetary scientists to reconsider the entire history of the Jovian system. If you were to chart the moons of Jupiter by size, you would expect to see a relatively smooth curve, a few very large objects, a greater number of medium-sized ones, and then a long tail of countless smaller bodies. This is the pattern we see in the asteroid belt and in the Kuiper belt, and it's the expected outcome of a natural accretion process where smaller pieces gradually clump together to form larger ones. Yet around Jupiter, this pattern is broken. There is a dramatic and jarring void. We have the four Galilean giants and then nothing, no moons even remotely close to their size. The next largest moons, like Amalthea and Himalaya, are absolutely dwarfed, measuring only a couple hundred kilometers across compared to the thousands of kilometers spanned by Ganymede or Callisto. This abrupt cutoff, this complete absence of intermediate-sized moons, is a statistical anomaly so severe that it cannot be mere chance. It points to a violent and disruptive event or series of events that systematically eliminated every single moon in that middle class. The leading theory to explain this missing middle class of moons involves a period of absolute chaos early in Jupiter's history, a time of catastrophic collisions. The thinking is that the region around the young Jupiter was far more crowded than it is today. The planet's powerful gravity would have captured numerous planetesimals and moon embryos, not just the four we see now. In this model, there wasn't just one Io or one Europa forming. There were likely several large moon-sized bodies sharing similar orbits. In the crowded, dynamically hot environment close to the giant planet, their orbits would have inevitably intersected, leading to a series of high-speed, moon-shattering impacts. These wouldn't have been gentle mergers, they would have been titanic crashes that utterly obliterated the colliding bodies, vaporizing rock and ice and grinding them down into a literal cloud of debris. This debris would have then had one of two fates. Some of it might have been reaccreted, but not into new mid-sized moons. Instead, the material would have been swept up by the surviving largest moons, making them even bigger. This could explain why Ganymede and Callisto are so massive. They may be the sole survivors of this lunar demolition derby, having grown by consuming their shattered rivals. The rest of the debris, particularly the fragments from collisions farther out, would have been ground down into the population of tiny, irregular moonlets we see today. Their irregular shapes are testament to their origin as collision fragments rather than peacefully formed worlds. This theory elegantly explains the size gap. The intermediate moons did exist, but they were violently destroyed, and their material was either absorbed by the giants or broken into pieces too small to ever reassemble. An alternative, or perhaps complementary, theory looks not at destruction, but at a stunted process of creation. It's possible that the conditions necessary to form moons in the first place were fundamentally different closer to Jupiter. The planet's immense gravity and its own rapid formation would have created a very specific environment in the surrounding gas and dust disk. This proto-lunar disk might have had a sharply defined edge or a particular density profile that only allowed for the formation of a few large moons very early on. Once those four massive bodies coalesced, they would have effectively vacuumed up all the available building material in their orbital zones, starving any potential later forming moons of the planetesimals and dust needed to grow to a substantial size. In this scenario, the intermediate moons weren't destroyed. They were never even allowed to form in the first place, prevented from growing past a certain small size by the gravitational dominance of their four massive older siblings. The answer likely lies in a combination of these processes. The early Jovian system was undoubtedly a violent and competitive place. The surviving Galilean moons themselves show evidence of this violent past. Callisto's ancient, crater-battered surface suggests it was a passive witness to the chaos, while Ganymede's complex geology hints at a more active and turbulent formation. The fact that we see this same size gap mirrored around Saturn, which also has a family of large moons and then a sharp drop-off to smaller ones, suggests this may be a universal outcome for gas giants. It implies that the processes of moon formation are inherently unstable and self-limiting. Once a few large bodies emerge, they either consume or prevent the rise of any competitors, leaving behind a silent record of celestial carnage. This missing middle class of moons is therefore a crucial clue, a fossilized imprint of the tremendous forces and fierce competition that shaped not just Jupiter's family, but planetary systems across the galaxy. And just when we thought we had seen the full extent of Jupiter's atmospheric fury, the Juno spacecraft turned its gaze toward the planet's poles and revealed a sight that was both breathtaking and utterly baffling. Before Juno, our view of Jupiter was largely confined to its equatorial region, the banded globe we see from Earth. The poles were a complete mystery hidden from our line of sight. What Juno found there defied all expectations and all known laws of fluid dynamics. Instead of a chaotic, turbulent mess, the cameras revealed stunningly organized geometric patterns of massive cyclones. At the North Pole, 8 smaller cyclones whirled tightly around a single, central giant storm, their centers tracing a near-perfect octagon. At the South Pole, 5 equally powerful cyclones performed the same intricate dance, their positions locked into a precise pentagon around a central vortex. These are not transient weather features, they are permanent, stable structures that have maintained their precise, polygonal formations for years, a phenomenon that, according to our current understanding of physics, simply shouldn't be possible. The sheer scale of these storms is difficult to comprehend. Each of the peripheral cyclones is itself a monster, with diameters matching that of the entire continental United States. They are not gentle breezes, they are hurricanes of unimaginable power, roaring with winds that scream at speeds comparable to their more famous equatorial cousins. And yet, despite their ferocious energy and close proximity to one another, they do not behave as any storm on Earth would. On our planet, when 2 powerful cyclones get this close, one of 2 things happens. They either merge into a single, larger storm, cannibalizing each other's energy, or they engage in a complex dance called the Fujiwara effect, where they orbit a common center before eventually flinging each other away. Jupiter's polar cyclones do neither. They are locked in place, maintaining a respectful and constant distance from their neighbors, spinning in a perfect, stable celestial ballet that has persisted without change since Juno first discovered them in 2016. This stubborn refusal to merge or disperse is the heart of the mystery. What invisible cage is holding these titanic storms in their perfect geometric formation? Scientists are actively piecing together the forces that could be creating this otherworldly stability. The leading theory involves a delicate and invisible balance between two competing powers, the inward pull of the central cyclone and the outward force created by the rapid rotation of the storms themselves. Imagine trying to push the same poles of several powerful magnets together. They resist, creating a stable, repulsive boundary between them. The cyclones may be generating a similar protective barrier through their own intense rotation. As each storm spins, it creates a ring of high-speed wind around its outer edge. Where these rings of wind from adjacent cyclones meet, they may be acting as moving walls, shearing against each other and creating a zone of repulsion that prevents the storm's cores from getting any closer and merging. It's a self-organizing system where the storm's own ferocious energy creates the very boundaries that contain them. But this alone doesn't explain the perfect polygons. For that, researchers are looking deeper toward a concept known as an anticyclonic ring. This is a large-scale, overarching vortex of wind that circulates in the opposite direction to the cyclones themselves. This larger background rotation may act like a guiding track, a subtle but powerful atmospheric river that helps to corral and position the individual storms, nudging them into the most stable geometric arrangement possible. The number of storms, 8 in the north, 5 in the south, could then be determined by the specific flow dynamics and available energy at each pole, with the system naturally settling into the most efficient polygonal pattern, much like bubbles foaming into a hexagonal honeycomb structure. This combination of local repulsion and a global guiding current might be the key to this enduring polar puzzle. The implications of solving this mystery stretch far beyond Jupiter itself. We are witnessing a completely new regime of fluid dynamics, one that operates in the absence of a solid surface to create friction, and under the influence of a rotation rate and planetary scale we cannot replicate in any lab on Earth. Understanding how these polygonal storms persist gives us a new set of physical rules for how atmospheres behave under extreme conditions. This knowledge is a master key, potentially helping us to interpret the complex weather patterns on other gas giants like Saturn, and even on the rapidly spinning exoplanets we are discovering light years away. Jupiter's polar cyclones are more than just a beautiful curiosity. They are a natural laboratory, showing us a form of order emerging from chaos that we never knew was possible, written in the clouds of a distant world. Even as we marvel at the geometric perfection of Jupiter's polar storms, the planet's entire visible face presents another, more fluid enigma, a world that is quite literally changing color before our eyes. The rich ochre belts and bright white zones that stripe its atmosphere are not the permanent features they appear to be in a single photograph. Over years and decades, these colossal bands can fade, darken, or even vanish entirely, only to later reappear. The Great Red Spot itself has deepened from a pale pink to an intense brick red over the past century. These chromatic shifts are not random. They are the visible symptoms of a deep and complex atmospheric system, yet the precise ingredients and recipes for Jupiter's ever-changing palette remain one of its most visually accessible but chemically perplexing mysteries. The fundamental reason for Jupiter's basic coloration lies in the chemistry of its cloud layers. The planet's atmosphere is not just hydrogen and helium. It's a bubbling soup of simple compounds like ammonia, ammonium hydrosulfide, and water, all swirling at different altitudes. The bright white bands, known as zones, are believed to be composed of fresh, reflective ammonia ice crystals lofted high into the upper atmosphere by rising air. The darker reddish-brown bands called belts are regions where the air is sinking. This subsidence clears away the high, white ammonia haze, allowing us to peer deeper into the atmosphere where more exotic chemicals reside. It is in these deeper, warmer layers that sunlight likely triggers chemical reactions that create the planet's famous colors. The leading candidates for these colorful compounds are complex molecules known as chromophores. On Jupiter, the most likely chromophores are thought to be compounds involving sulfur, phosphorus, or a class of complex hydrocarbons called tholins. Tholins are not a specific compound but a family of reddish-brown, gunk-like substances formed when simple gases like methane and ammonia are exposed to ultraviolet light. The process is akin to planetary photochemistry, a form of sunburn where solar radiation breaks apart simple molecules and they recombine into more complex, darker-colored polymers. This could explain the ruddy hues of the belts and the great red spot. These are essentially vast, planet-sized patches of atmospheric sunburn, revealed as the overlying white clouds subside. However, the fact that the colors change so dramatically over time suggests this process is far from static. A prominent dark belt can suddenly lighten, becoming almost indistinguishable from a white zone. The entire south equatorial belt, a major feature, has famously disappeared entirely on several occasions, most recently in 2010, only to gradually return months later. These events point to a dynamic interplay between chemistry and atmospheric dynamics. A major upheaval in the cloud deck, perhaps a powerful thunderstorm system erupting from below, could dredge up fresh, colorless material from the depths, temporarily covering or diluting the darker chromophores and causing a belt to fade. Conversely, a period of calm and sustained subsidence might allow solar UV radiation to more effectively cook the exposed compounds, deepening their color significantly. The Great Red Spot provides the most iconic example of this color mystery. Its hue has varied dramatically since detailed observations began, ranging from a faint salmon pink to the deep, intense red we see today. One compelling theory suggests that the storm's changing color is directly tied to its physical evolution. As the anticyclone has shrunk over the past century, it has also intensified, with wind speeds increasing around its periphery. This increased storm fury might be powerful enough to dredge up greater amounts of material from deeper within the planet's atmosphere. If the reddish chromophores are formed at a specific, warmer level deeper down, then the storm could be acting like an elevator, bringing a more concentrated supply of these colorants up into the high-altitude sunlight where we can see them, explaining its recent reddening. An alternative, or perhaps complementary, theory involves the effects of altitude and temperature on the chemical reactions themselves. The compounds responsible for the colors might go through different phases or change their optical properties depending on how high they are lifted and how cold they become. A compound that is red when warm and at a moderate depth might appear white or be inactive when chilled at higher altitudes. Therefore, a shift in the vertical structure of the cloud decks, a warming or cooling, a lifting or subsiding, could directly alter the color we perceive without any change in the actual chemical composition. It becomes a three-dimensional puzzle where we are only seeing the final, two-dimensional result. Despite decades of observation and data from spacecraft like Juno, no single theory can yet fully explain the timing, location, or intensity of Jupiter's color changes. The planet's atmosphere is a giant, chaotic chemical reactor with variables of pressure, temperature, solar irradiation, and vertical transport all in constant flux. Each color shift is a clue, a fleeting glimpse into the immense engine of circulation and chemistry raging beneath the clouds. Solving this mystery requires untangling a web of cause and effect that operates on a planetary scale, where a change in one part of the globe can ripple through the entire system and manifest as a subtle shift in hue, a visual testament to the dynamic and living nature of this colossal world. For centuries, the magnificent bands and roaring jet streams of Jupiter's atmosphere were believed to be just that, atmospheric, a spectacular but shallow weather phenomenon confined to the cloud tops we could see. It seemed logical. On Earth, our jet streams are relatively thin rivers of air, a few miles deep at most, driven by solar heating. Why would Jupiter's be any different? This assumption was completely upended when the Juno spacecraft began its precise measurements of the planet's gravity field. By tracking tiny wobbles in the spacecraft's orbit, scientists could map the distribution of mass deep within the giant planet, and what they found was astonishing. The powerful east-west jet streams, which appear as the borders between the planet's colorful bands, are not skin-deep. They are immense planetary scale structures, massive rivers of flowing material that extend thousands of kilometers downward, reaching at least 3,000 kilometers beneath the cloud tops. This discovery shattered the old, shallow weather model and revealed that Jupiter's beautiful surface is merely the visible tip of a deeply rooted, planet-wide circulatory system. The depth of these jets is the first part of the mystery. Their stability is the second. On a planet with no solid surface to create friction, what prevents these incredibly deep currents from simply dissipating their energy or breaking down into chaos over such vast distances? The answer appears to lie in the exotic nature of the material they are flowing through. As these jets plunge downward, they move through hydrogen gas that is being subjected to ever-increasing pressure. Around 1,000 kilometers down, the pressure becomes so immense that the hydrogen undergoes a profound phase change. It ceases to behave like a gas and transitions into a fluid metallic state, a sea of electrically conducting liquid. The incredible finding from Juno's gravity data is that the jet streams don't stop at this boundary. They continue right on through, penetrating deep into this metallic hydrogen ocean. This means the forces that generate and sustain these jets are powerful enough to operate not just in a gaseous atmosphere, but within a churning metallic fluid, a realm of physics we can scarcely replicate on Earth. This revelation forces a complete rethink of what drives Jupiter's most obvious features. It means the jet streams are not primarily powered by the sun's energy, like weather on Earth, but are instead manifestations of the planet's own internal dynamics and its ferocious rotation. The entire planet, from its cloud tops to its deep interior, is spinning as a single, cohesive unit in what scientists call rigid body rotation. The jets themselves are relatively small perturbations on top of this overall rotation, but they are driven by colossal forces emerging from within. The leading theory suggests that the energy powering these deep flows comes from the planet's own immense internal heat, left over from its formation. This heat generates powerful convection currents, with hotter material rising and cooler material sinking. On a rapidly spinning sphere like Jupiter, these upwelling and downwelling motions are whipped by the Coriolis effect into the organized, parallel bands we see at the surface. The jets are essentially the surface expression of these planet-wide heat engines, with their roots anchored in the thermal chaos of the interior. The penetration of these flows into the metallic hydrogen layer has staggering implications for Jupiter's magnetic field, the strongest in the solar system. Magnetic fields are generated by the movement of electrically conductive fluids. We now know that the jet streams are moving this conductive material, the metallic hydrogen itself, on a massive scale. This means the same deep flows that create the striped appearance of the planet are also directly involved in generating its monstrous magnetic field. The dynamics of the jets and the dynamo are inextricably linked, a feedback loop of fluid motion and electromagnetic force operating on a scale that dwarfs our entire planet. The lopsided and complex nature of Jupiter's magnetic field, with its intense patches like the Great Blue Spot, is likely a direct result of this turbulent, deep-seated circulation within the metallic ocean. We are not looking at two separate systems, an outer weather layer and an inner dynamo, but a single, deeply interconnected engine where atmospheric beauty is forged in the metallic depths below. But understanding Jupiter's internal engine and its present-day dynamics inevitably leads us back to the very beginning, to the momentous question of how this Titan was built in the first place. The mystery of Jupiter's formation timeline is not just about dating an ancient event. It's a fundamental debate that forces us to choose between two completely different narratives for the origin of our entire solar system. For decades, the textbook story was one of slow and steady growth, but a revolution in planetary science has introduced a compelling alternative, a dramatic, rapid-fire birth that would have reshaped the infant solar system in its image. The evidence for each theory is etched into the very fabric of the planets, and Jupiter holds the key. The traditional model, known as core accretion, paints a picture of patient, gradual construction. In this scenario, the young sun was surrounded by a swirling disk of gas and dust. Within this protoplanetary disk, tiny particles of dust and ice began to stick together, first through static electricity, then through their own weak gravity. Over several million years, these planetesimals collided and merged, slowly building a solid core of rock and ice. Once this core reached a critical mass, perhaps 10 to 20 times that of Earth, its gravitational pull became powerful enough to suddenly and rapidly capture enormous amounts of hydrogen and helium gas from the surrounding disk. In this model, Jupiter's growth was a two-part process, a slow buildup of a solid core, followed by a rapid, runaway acquisition of gas. This theory suggests it could have taken anywhere from 3 to 10 million years for Jupiter to reach its full size, a relative eternity in the fast-paced early solar system. However, this elegant story began to develop cracks. The core accretion model relies on a vast reservoir of gas being available for a long time. But observations of young stars elsewhere in the galaxy suggest that these primordial gas disks tend to dissipate, blown away by the intense radiation from the newborn star within just 1 to 3 million years. If the gas disk vanishes too quickly, a slowly forming Jupiter would have run out of building materials before it could become a true giant. This timing problem gave rise to a far more dramatic and disruptive theory: gravitational disk instability. This process suggests that Jupiter could have formed not slowly from the bottom up, but almost instantaneously from the top down. In this scenario, instabilities within the cold, dense outer regions of the protoplanetary disk could have caused large swaths of gas to collapse directly under their own gravity, rapidly coalescing into a giant planet without the need for a large solid core to start the process. This could potentially happen in a mere 1,000 years, a blink of an eye on the cosmic clock. The implications of these two timelines are profound and reach far beyond Jupiter itself. A rapidly formed Jupiter, through gravitational collapse, would have been a towering presence in a solar system that was still a chaotic construction site. Its immense gravity would have acted as a definitive barrier, effectively carving the disk into an inner and outer region and preventing material from mixing. This could explain the clear chemical divide we see in the solar system today, with rocky, water-poor planets like Earth and Mars in the inner system and water-rich, gaseous giants in the outer system. A slow-forming Jupiter, on the other hand, would have allowed for more mixing of material across the disk before it grew large enough to dominate, a scenario that makes the current stark division between the inner and outer planets more difficult to explain. The most compelling evidence in this debate may come from the planet's own structure, specifically the data on its potentially fuzzy, diluted core returned by the Juno spacecraft. The core accretion model typically predicts a dense, compact core, the original seed around which the gas gathered. The gravitational disk instability model, in its purest form, might predict no large core at all, as the planet forms directly from gas. Juno's discovery of a partially dissolved, extended core that blends into the metallic hydrogen layer presents a fascinating middle ground that seems to challenge both ideas. Some scientists argue this supports a hybrid scenario, a rapid formation via disk instability that was then followed by the accretion of solid planetesimals, which sank toward the center and began to form a core. Others suggest it points to a colossal impact in Jupiter's youth, where a massive planetary embryo slammed into the planet's heart and shattered its original compact core, mixing the heavy elements throughout the inner region. The true story of Jupiter's birth is therefore written in the obscure chemistry and structure of its deep interior, a hidden record of the violent and competitive environment from which our solar system emerged. And this brings us to one of the most profound and counterintuitive discoveries about the giant planet, the startling realization that its powerful magnetic field is not the orderly, symmetrical structure we expected, but is instead deeply lopsided and irregular. For centuries, we've modeled planetary magnetic fields using a simple concept, the dipole. Imagine a giant, perfectly straight bar magnet running through the center of a planet, neatly aligned with its axis of rotation, with orderly field lines flowing from the South Pole to the North Pole in a graceful, symmetrical arc. Earth's field is a reasonably good, though not perfect, example of this. For a massive, rapidly spinning ball of fluid like Jupiter, scientists expected its magnetic field to be an even more perfect dipole, smoothed into symmetry by the planet's ferocious rotation. The data from the Juno mission proved this assumption spectacularly wrong. Juno's detailed maps revealed a magnetic field that is chaotically uneven, a tangled mess of intense hotspots and surprisingly weak regions. The most shocking asymmetry is between the northern and southern hemispheres. The field in the north is a complex and convoluted jungle of flux, with multiple intense magnetic spots scattered across the hemisphere. The south, by comparison, is significantly less complicated and more organized, but the crown jewel of this magnetic weirdness is a feature scientists have nicknamed the Great Blue Spot. This isn't a visual storm, you can't see it with a camera. It's a concentrated patch of intensely powerful magnetic flux located near Jupiter's equator, but offset well to the north of the planet's rotation axis. This single region contains an astonishing amount of the planet's total magnetic power, acting like a local, supercharged magnet glued bizarrely to one side of the planet. This profound lopsidedness defies our current models of how planetary dynamos are supposed to work. A dynamo, the process that generates a magnetic field, requires three ingredients: a convecting fluid, rotation, and electrical conductivity. Jupiter has all three in spades with its vast ocean of swirling metallic hydrogen. Our models predicted that Jupiter's rapid 10-hour rotation would force this dynamo into a state of beautiful symmetry, efficiently organizing the magnetic field into a smooth, dipole-dominated structure. The reality is a field that looks like it was generated by a dynamo that's only working properly in one half of the planet. This forces a complete re-evaluation of the conditions deep within Jupiter's interior. The leading theory to explain this bizarre asymmetry points to the nature of the fluid itself and the environment in which the dynamo operates. On Earth, our dynamo functions in a spherical shell of molten iron that surrounds a solid inner core. This solid inner core may play a key role in stabilizing and symmetrizing our magnetic field. Jupiter, however, appears to have no such solid anchor at its center. Its core is likely diluted and fuzzy, a region where heavy elements are mixed into the fluid metallic hydrogen. Without a solid core to provide a stable boundary and help organize the flow, the dynamo may be operating in a much more chaotic and turbulent manner. Furthermore, the transition from gaseous hydrogen to metallic hydrogen is not a sharp boundary at a single depth. It's probably a vast, diffuse region where the conductivity of the fluid changes gradually. This means the dynamo is not confined to a neat spherical shell, but could be active throughout a large portion of the planet's interior, with different depths generating magnetic fields that interfere with each other in complex and uneven ways. The location of the Great Blue Spot offers another vital clue. Its position suggests it might be rooted to a specific, stable structure deep within the planet, perhaps a concentrated region of heavier elements left over from Jupiter's formation, or a particularly powerful upwelling or downwelling in the metallic hydrogen ocean. This persistent anomaly could be distorting the flow of the electrically conducting fluid right at the source, creating a permanent kink in the magnetic field that then manifests as this intense, localized spot. The immense pressures at Jupiter's heart might also be creating exotic states of matter, like solid metallic hydrogen, which could possess wildly different electrical properties and further disrupt the symmetry of the dynamo process. This magnetic asymmetry is more than just a curiosity. It's a direct window into the obscure and extreme physics occurring thousands of miles below the clouds, showing us that even the most fundamental planetary processes can operate in ways we are only beginning to imagine. And just when we thought we had a handle on the complex chemistry of Jupiter's clouds, another atmospheric ingredient began behaving in a way that defied all predictions, creating what scientists call the missing ammonia mystery. Ammonia, a compound of nitrogen and hydrogen, should be abundant and well mixed throughout Jupiter's upper atmosphere. It's a key player in the planet's cloud formation, expected to condense into bright white ice crystals at high altitudes, creating the reflective zones we see. Yet, when researchers began mapping its global distribution using instruments like the Juno spacecraft's microwave radiometer, they found something profoundly strange. The ammonia wasn't uniformly distributed like a well-stirred soup. Instead, it was bizarrely depleted in certain regions, almost as if some invisible atmospheric vacuum was actively sucking it down into the deep, hidden layers of the planet far beyond our view. This isn't a minor discrepancy, it's a major imbalance in the expected chemical inventory of a gas giant. Jupiter formed in the cold outer solar system where ammonia ice was plentiful. The planet should have accreted vast quantities of it, and its powerful mixing currents should keep it suspended in the upper atmosphere. Finding deep, localized shortfalls of this fundamental compound suggests that our understanding of Jovian meteorology is missing a crucial piece of the puzzle. The prevailing theory points to a previously unknown and violent form of precipitation, a meteorological process so efficient at scavenging ammonia that it can strip it from entire sections of the atmosphere and bury it thousands of miles below. The leading suspect in this atmospheric heist is a weather phenomenon we briefly touched on earlier, mushballs. These are not gentle snowflakes or even hard hailstones as we know them. In the frigid upper reaches of Jupiter's atmosphere, where temperatures are low enough to freeze water, ammonia acts as a potent antifreeze. It mixes with water to form a slushy ammonia-water cocktail that can remain liquid at much lower temperatures than pure water. Within towering thunderstorm systems, powerful updrafts carry water vapor and ammonia gas high into the atmosphere where they freeze onto tiny seeds, beginning the formation of a hailstone. But in this alien environment, the hailstone doesn't solidify. It grows into a massive, slushy ball of ammonia water ice, a mushy iceberg that can be a foot or more across. Once these massive mushballs form, they begin to fall, and they don't stop easily. Their considerable weight gives them immense momentum, allowing them to plunge through layer after layer of the atmosphere. They fall through regions where the temperature and pressure are far too high for such a concoction to normally exist, traveling hundreds of miles downward into the planet's warm interior. Eventually, they reach a depth so hot that the mushball completely evaporates, releasing its captured cargo of ammonia and water vapor into a deep atmospheric reservoir, effectively sequestering it from the upper atmosphere where we can detect it. This process creates a complete, previously invisible cycle, a vertical conveyor belt that transports volatiles from the top of the atmosphere to its abyssal depths, explaining the mysterious depletions observed from orbit. This theory elegantly solves the mystery of the missing ammonia, but it also helps explain another long-standing puzzle, the source of Jupiter's shallow lightning. These high-altitude electrical storms occur in places far too cold for pure water clouds to form and generate lightning through charge separation. The mushball scenario provides the missing link. The formation of these slushy hailstones within the cold, ammonia-rich clouds is itself a violent process involving collisions between different phases of ice and slurry. This turbulent action within the storm clouds is likely the very mechanism that separates electrical charge, generating the flashes of lightning that Juno saw near the poles. Therefore, the same process that steals the ammonia mushball precipitation is also responsible for creating the unexpected lightning, tying two enigmatic phenomena together into a single dramatic meteorological cycle. The implications of this discovery stretch far beyond accounting for a missing chemical. It reveals a Jovian weather system that is far more complex and vertically integrated than we ever imagined. We are not looking at a simple, shallow weather layer, but a deeply connected system where events in the upper clouds can have direct consequences thousands of kilometers below, and vice versa. This ammonia cycle is a stark reminder that the processes shaping giant planets are not just scaled-up versions of Earth's weather. They are governed by alien physics and chemistry, where common compounds like water and ammonia behave in extraordinary ways under extreme pressure. Cracking the case of the missing ammonia hasn't just solved one mystery. It has opened our eyes to a whole new world of atmospheric dynamics, where slushy icebergs fall from the sky and hide the secrets of the planet in its deep, hot heart. From the churning depths of its metallic ocean to the shocking cold of its high-altitude lightning, Jupiter consistently defies our expectations of how energy should behave on a planetary scale. But perhaps one of its most pervasive and puzzling energy mysteries doesn't involve a lack of power, but rather a mysterious and unexplained surplus high above the clouds. Scientists refer to this enigma as Jupiter's energy crisis, and it revolves around a simple, baffling temperature reading. Based on all known physics, the upper layers of Jupiter's atmosphere, its thermosphere, should be intensely cold, plunging to a frigid -150 degrees Fahrenheit. The Sun is simply too far away to provide significant warmth at that altitude. Yet, when we take the temperature, we find that this region is actually a roaring furnace, heated to a staggering 800 degrees Fahrenheit, a value that rivals the surface of the planet Venus. This 900-degree discrepancy between prediction and reality means there is a colossal, hidden heater pumping energy into Jupiter's upper atmosphere, and for decades its identity has remained completely unknown. This isn't a minor accounting error, it's a fundamental failure in our understanding of planetary energy budgets. The crisis is that we cannot identify the fuel source for this incredible heat. On Earth, our upper atmosphere is heated by the Sun's extreme ultraviolet radiation, but Jupiter is 5 times farther from the Sun, receiving only a minuscule fraction of that energy nowhere near enough to account for the observed temperatures. The planet's own internal heat, which drives the weather below, is trapped by the dense lower atmosphere and cannot rise to these heights. So where is all this energy coming from? It's as if we walked into a perfectly insulated room with no fireplace or radiator and found it was blisteringly hot inside with no obvious explanation. This thermal anomaly suggests that Jupiter's atmosphere is host to a powerful and efficient energy transfer mechanism that we have not yet learned to see. The primary suspect in this mystery is the planet's own ferocious auroras. These dazzling light shows at the poles are the most powerful in the solar system, and they represent a tremendous dump of energy. Charged particles funneled by Jupiter's magnetic field slam into the atmospheric gases, and their immense kinetic energy is converted into heat, light, and motion. It seemed like a perfect solution. The auroras heat the polar regions, and this warmth then circulates toward the equator, solving the energy crisis. However, when scientists modeled this process, they hit a wall. The heat generated by the auroras, as immense as it is, appears to be trapped near the poles. The atmosphere on a giant planet is not efficient at redistributing this energy across the globe. It should stay concentrated in the high latitudes, leaving the equatorial regions much colder than they actually are. The observed heat is global, but the prime suspect's influence is local, creating a frustrating dead end. This contradiction has forced researchers to look for other, more exotic explanations. One compelling theory points toward the planet itself as a giant vibrational energy source. The idea is that Jupiter's lower atmosphere is a cacophony of powerful waves, acoustic waves, gravity waves, and pressure waves generated by the immense storms and turbulence raging in the cloud decks far below. These are not gentle ripples, they are planet-scale oscillations like the deep, resonant notes from a colossal musical instrument. As these waves travel upward into the ever-thinning atmosphere, they grow in amplitude until they eventually break, much like an ocean wave crashing on a shore. When they break, they release all their pent-up energy directly into the upper atmosphere as heat. This process could act as a planet-wide heating system, delivering warmth from the turbulent interior directly to the surprisingly hot outer layers, bypassing the need for inefficient circulation from the poles. Another fascinating hypothesis looks to the planet's magnetic field as the delivery mechanism for this mysterious energy. Jupiter's magnetic field is not a static cage. It is dynamic, constantly vibrating and oscillating. These vibrations can create electromagnetic waves that propagate along the magnetic field lines, carrying energy from the inner magnetosphere all the way down into the upper atmosphere. When these waves hit, they could cause the charged particles in the atmosphere to jiggle violently, a motion that translates directly into heat. This process could effectively distribute energy along magnetic longitudes, helping to explain how warmth might be spread more evenly from the poles toward the equator, bridging the gap that the simple auroral heating model could not cross. We are essentially considering the possibility that Jupiter is cooking its upper atmosphere with microwaves generated by its own magnetic dynamo. Solving this energy crisis is about far more than just balancing a thermal equation for a single planet. This phenomenon is not unique to Jupiter. We see similar unexplained heating in the upper atmospheres of Saturn, Uranus, and Neptune. It appears to be a fundamental property of gas giants, a universal process that our current models of atmospheric physics are completely missing. By cracking the case on Jupiter, we would be unlocking a master key to understanding the climate and energy flow of an entire class of planets, both within our solar system and among the thousands of gas giants we've discovered orbiting other stars. The mystery forces us to consider entirely new ways that energy can be generated, transferred, and dissipated in atmospheres without solid surfaces, teaching us that the rules of planetary science are far more complex and wondrous than we ever imagined. For all its fame and centuries of observation, the Great Red Spot holds onto one of its most visually striking secrets, the source of its deep brick red hue. This isn't a mere question of aesthetics. The color is a direct chemical clue to the complex processes churning within the storm and deep beneath Jupiter's clouds. Yet, despite our most advanced telescopes and spacecraft flying through its periphery, the exact compound, or cocktail of compounds responsible for this iconic color has stubbornly eluded detection, making its chromatic signature one of the planet's most persistent and fascinating puzzles. The challenge begins with the nature of the light we use to analyze it. Spectrometers, our primary tools for remote chemical analysis, work by identifying the unique fingerprints that molecules leave on light. Different compounds absorb specific wavelengths of light, creating dark lines in a spectrum that act like a barcode for a chemical. However, the Great Red Spot's coloring agent, or chromophore, seems to be a master of disguise. Its spectral signature is remarkably broad and smooth, lacking the sharp, distinctive absorption features that would make it easy to identify. It's as if we're trying to identify a specific person in a crowd, but they're wearing a perfectly generic costume that blends in with everyone else. This broad, featureless absorption simply tells us that something is there, soaking up the blue and green light to give the spot its reddish appearance, but it refuses to give up its specific identity. This ambiguity has opened the door to a host of compelling theories, each with its own merits and complications. One long-standing hypothesis points to phosphorus. The idea is that phosphorus compounds, perhaps phosphine gas rising from the planet's deep interior, could be broken apart by ultraviolet light from the sun high up in the spot's upper reaches. These broken fragments could then recombine into allotropes of phosphorus, such as red phosphorus, which is known for its deep red color. It's a plausible idea, but the chemical pathways to form significant quantities of it in the Jovian atmosphere are complex and not yet fully demonstrated. Another strong candidate involves sulfur. Jupiter's atmosphere is rich in hydrogen sulfide and other sulfur-bearing compounds, and the moon Io constantly volcanoes sulfur dioxide into the Jovian system. Complex sulfur compounds or polymers could easily possess the right chemical properties to create that ruddy color. There's also the fascinating possibility of tholins, a class of complex organic molecules that are not a single compound but a family of reddish, tar-like substances. Tholins are created when simple, common compounds like methane and ammonia are exposed to ultraviolet light, effectively giving them a planetary scale sunburn. This photochemical process is known to occur on other bodies in the outer solar system, like Saturn's moon Titan, giving its atmosphere a characteristic orange haze. The Great Red Spot, with its high-altitude clouds exposed to intense sunlight, could be a perfect factory for such tholin production. The mystery deepens when we consider that the spot's color isn't constant. Historical records and modern observations show it has varied dramatically over the centuries, shifting from a pale salmon pink to the intense, deep red we see today. This variability suggests the color isn't caused by a single, static compound, but is instead the result of an active chemical process that is sensitive to environmental conditions. The leading theory for these changes ties them directly to the storm's physical evolution. As the Great Red Spot has shrunk and intensified over the past century, its swirling winds may have grown powerful enough to act as a colossal elevator, dredging up greater amounts of material from deeper within the planet's atmosphere. If the reddish chromophores are formed at a specific, warmer level deeper down, then the storm could be bringing a more concentrated supply of these colorants up into the high-altitude sunlight where we can see them, explaining its recent reddening. Conversely, a period of weaker storm activity or an influx of fresh, white ammonia ice crystals from above could dilute the color, causing it to fade to a paler hue. This creates a dynamic picture where the spot's color is not a permanent feature, but a living thermometer and flow meter. Its shade a visible gauge of the storm's power and its ability to churn up the hidden depths of Jupiter's mysterious atmospheric chemistry. We've explored how Jupiter's immense internal heat and complex chemistry drive its weather, but the giant planet has another, far more subtle trick up its sleeve. It can literally cook itself with microwaves. This isn't science fiction. It's a bizarre and unexpected form of radiation emanating from deep within its atmosphere that has left scientists thoroughly perplexed. When we peer at Jupiter using instruments tuned to microwave frequencies, we aren't just seeing reflected sunlight or simple thermal heat. We are detecting emission from within the cloud layers themselves. The pattern of this microwave radiation should, in theory, paint a clear and predictable picture of the planet's internal temperature structure and chemical composition. Instead, the maps we get are strange and confounding, revealing bright and dark spots that defy our models and point to either unknown atmospheric processes or fundamental gaps in our understanding of how energy behaves in such an extreme environment. The mystery begins with the basic physics of microwave emission from a gas giant. At these wavelengths, we are effectively seeing the thermal radiation coming from depths of a few dozen to a few hundred kilometers below the visible cloud tops. Ammonia gas is the key player here. It's exceptionally good at absorbing microwave radiation. In a perfectly uniform and predictable atmosphere, the amount of ammonia at different depths would create a smooth, predictable gradient in the microwave brightness we detect. Areas with more ammonia should appear darker as the gas absorbs the upwelling radiation from below. Areas with less ammonia should appear brighter, allowing more of the internal thermal radiation to leak out into space. When the Juno spacecraft used its microwave radiometer to map this emission, scientists expected a relatively smooth and symmetrical map, perhaps slightly brighter at the equator and darker at the poles. What they found was anything but. The microwave maps are a patchwork of bizarre anomalies. There are inexplicably bright bands that ring the planet alongside startlingly dark patches, particularly near the equator. This chaotic and uneven distribution means that the ammonia itself is not mixed evenly, as all our atmospheric circulation models had assumed. Something is causing massive, localized concentrations and depletions of this important gas on a global scale. The dark spots indicating areas where ammonia is highly depleted were particularly shocking. It's as if colossal, invisible funnels are sucking the ammonia down into the deep atmosphere, creating vast chemical deserts in the middle of the cloudy layers. This was the first major clue that our simple models of a well-stirred atmospheric soup were completely inadequate for a dynamic world like Jupiter. So what could be causing this strange patchwork of microwave hot and cold spots? The leading theory brings us back to the concept of atmospheric circulation, but on a far more dramatic and three-dimensional scale than we previously imagined. Jupiter's weather is not a shallow phenomenon. It operates from the cloud tops all the way down to the abyss. The bright microwave regions could be areas of powerful, widespread upwelling. Here, colossal plumes of warm, ammonia-poor air are rising from the deep interior. Because this air comes from below, it has had its ammonia scrubbed out by processes like mushball precipitation, and as it rises, it carries this relative dryness with it. This allows more of the planet's internal heat to radiate out unimpeded, creating a bright microwave signature. Conversely, the dark microwave bands could be zones of large-scale subsidence, where colder, ammonia-rich air is sinking down into the planet. This dense, sinking air would be heavily laden with ammonia gas, which acts like a thick blanket, absorbing the microwave radiation trying to escape from below and making those regions appear dark to our instruments. This creates a picture of a planet breathing on a gigantic scale, with entire bands of the atmosphere rhythmically rising and falling, redistributing heat and chemicals in a way that leaves a distinct and puzzling imprint in the microwave spectrum. The planet's rapid rotation likely whips these upwellings and downwellings into the organized banded structure we see, but the incredible power driving this circulation remains rooted in the intense heat boiling up from Jupiter's interior. However, there is an even more intriguing possibility that goes beyond simple gas circulation. The peculiarities of the microwave data might not be caused solely by ammonia distribution, but by something fundamentally altering the way the radiation itself propagates through the atmosphere. The intense, chaotic magnetic field we discussed earlier could be playing a direct role. Jupiter's atmosphere is filled with plasma and charged particles, especially in the polar regions influenced by the auroras. It's possible that powerful electromagnetic plasma waves generated by the magnetosphere are interacting with the atmospheric gases and influencing how microwaves are emitted or absorbed. In certain regions, these waves could be enhancing the emission, making areas appear artificially bright, while in others they could be suppressing it. Another fascinating idea involves the water clouds deep below the ammonia layer. Water is also a very effective absorber of microwave radiation. The complex and turbulent structure of these deep water cloud systems, which we cannot see directly, could be casting a kind of shadow in the microwave spectrum, creating the dark patches we observe from above. We might be seeing the ghostly imprint of Jupiter's deepest, most violent weather, patterns of storminess occurring so far down that they can only reveal themselves by subtly altering the radiation that passes through them on its way out into space. Unraveling this microwave mystery is therefore like trying to solve a layered puzzle, where the answer could lie in chemistry, in fluid dynamics, or in the complex interplay of matter and energy under conditions we are only beginning to understand. While the swirling geometric patterns at Jupiter's poles showcase a breathtaking form of atmospheric order, the entire planet is itself a monument to one of the most fundamental and violent forms of motion in the universe: rotation. Jupiter spins with a ferocious, almost terrifying speed, completing a full rotation on its axis in just under 10 hours. Given its colossal size, a planet wide enough to fit over 11 Earths across its equator, this velocity is staggering. The cloud tops at its equator are hurtling through space at approximately 28,000 miles per hour. This incredible rotational energy doesn't just create the planet's oblate shape, flattened at the poles and bulging at the equator. It is the central engine driving everything we see, from the banded jet streams to the stability of the Great Red Spot. Yet, for a world that is almost entirely fluid, with no solid surface to act as a brake, the persistence of this rapid spin across billions of years presents a fascinating physical puzzle of its own. The mystery of Jupiter's rotation is twofold. The first part is a question of conservation. How has it maintained this dizzying speed for so long? In the vacuum of space, with nothing to rub against, a spinning object will naturally conserve its angular momentum, a principle that explains why an ice skater spins faster when they pull their arms in. Jupiter formed from a collapsing cloud of gas and dust in the early solar nebula, and as that cloud contracted, its spin increased dramatically, just like that ice skater. The planet has been spinning with that primordial energy ever since. But this leads to the second, more complex part of the mystery. If the entire planet is spinning as a single unit, why do different parts of its atmosphere appear to rotate at slightly different speeds? This phenomenon, known as differential rotation, means that the planet does not have a single, unified rotation period. The equatorial regions complete a rotation about 5 minutes faster than the higher latitudes. While 5 minutes might seem trivial over a 10-hour day on the scale of a gas giant, this difference represents a tremendous shearing force, a constant friction between colossal atmospheric bands moving at different velocities. This differential rotation is the key to understanding Jupiter's visible weather. The fast-moving equatorial region and the slower-moving polar regions create a system of powerful jet streams at the boundaries between them. The planet's rapid overall rotation through the Coriolis effect then forces these winds to organize into the stable, parallel eastward and westward jets that create its iconic banded appearance. It's a self-reinforcing system where the rotation drives the winds, and the structure of those winds, in turn, is a direct manifestation of the rotation. However, the Juno mission's gravity measurements added a stunning new layer to this story. They revealed that these jet streams are not shallow weather features. They are thousands of kilometers deep, extending through the entire molecular hydrogen layer and into the planet's ocean of metallic hydrogen. This means the differential rotation we see at the cloud tops is not merely a surface-level weather pattern. It is a fundamental characteristic of the planet's entire fluid interior, a signature of deep-seated dynamics. This profound depth forces a critical question: what is the anchor for this entire system? On a planet with no solid surface, what determines the planet's overall rotation rate? The answer is believed to lie in the deepest interior, possibly with the planet's magnetic field. The magnetic field is generated by the motion of electrically conductive fluid, the metallic hydrogen, in the deep interior. This dynamo process is thought to be tied to the planet's bulk rotation. Essentially, the rotation rate of the magnetic field, which is very consistent, may represent the true core rotation rate of Jupiter itself. The slightly varying rotation speeds we see at the cloud tops are then just the outermost expression of much slower and more complex circulatory patterns within the deep fluid layers, all superimposed on this stable, rapid bulk spin. Jupiter's 10-hour rotation is thus the heartbeat of a fluid world, a rhythm set in its hidden heart that pulses through every layer of its being, dictating the beautiful and chaotic dance of its clouds. After exploring the complex chemical cycles and swirling storms that shape Jupiter's visible face, we must now dig even deeper into the planet's very composition, where another fundamental mystery awaits. When we analyze the raw ingredients that make up Jupiter, we find a puzzling discrepancy that challenges our core understanding of where and how the planet was built. Based on the well-established composition of the Sun, which we use as a benchmark for the primordial solar nebula from which all planets formed, we can predict how much of each element should be present in a gas giant like Jupiter. For the most abundant elements, hydrogen and helium, this holds true. But when we look at what astronomers call metals, meaning all elements heavier than helium, the story becomes strange. Jupiter shows a curious and consistent pattern. It is enriched in some heavier elements like carbon and nitrogen, but surprisingly depleted in others, most notably oxygen and several noble gases. This isn't a uniform enrichment, it's a selective filtering, as if some elements were welcomed into the planet's construction while others were mysteriously turned away at the door. This pattern of selective enrichment is a profound clue. It tells us that Jupiter did not simply form by swallowing a representative sample of the early solar nebula. Something intervened to alter the chemical recipe, and scientists have two compelling but very different theories to explain this cosmic pickiness. The first theory places the blame on Jupiter's own frigid environment during its formation. Beyond the frost line in the early solar system, temperatures were cold enough for volatile compounds to freeze into solid ice grains. We know that water freezes, but so do other compounds like ammonia and methane, creating what are known as clathrate hydrates, essentially cages of water ice that can trap other gas molecules inside them. This theory suggests that the elements Jupiter is enriched in, like carbon and nitrogen, were easily locked away in these icy traps. Carbon, for instance, would have been readily captured in methane ice, while nitrogen would be trapped in ammonia ice. These ices then acted as efficient delivery vehicles, ensuring these elements were incorporated into the planetesimals that eventually built Jupiter's core. Conversely, the elements that are missing, particularly oxygen and the noble gases like argon, krypton, and xenon, are far more reluctant to be captured. Oxygen's primary carrier is water ice, but for it to freeze out completely requires extremely cold and specific conditions. Noble gases, by their very non-reactive nature, largely refuse to form stable compounds or get trapped in ice cages at all. They prefer to remain as free-floating gases. In this selective trapping model, when the time came for Jupiter to accrete its gas envelope, it was gathering material from a nebula that had already been chemically filtered by this icy process. The gases available for accretion were already depleted in these stubborn elements, imprinting that deficiency directly onto the finished planet. The second major theory is far more dramatic and points to a catastrophic event in Jupiter's infancy. This model suggests that Jupiter's original composition did indeed match the solar nebula, but it suffered a colossal impact early in its life. The idea is that a massive planetary embryo, perhaps the size of Uranus or Neptune, slammed into the young Jupiter. The energy from such an unimaginable collision would have been staggering, vaporizing not only the impactor but also blasting away a significant portion of Jupiter's own primordial atmosphere. This process, known as impact erosion, would have preferentially stripped away the lighter, more volatile elements, precisely those noble gases and oxygen that are now missing. The elements that are enriched being locked away in more solid, less volatile form within the planet's core or deeper layers, would have been largely spared from this atmospheric blow-off. This theory paints a picture of a violent solar system childhood, where Jupiter's current chemical identity was forged in a single, planet-shattering collision that forever altered its elemental makeup. Distinguishing between these two theories is more than an academic exercise. It is vital for reconstructing the earliest chapters of our solar system's history. The selective trapping model supports a relatively calm and orderly formation process where Jupiter grew steadily by accreting pre-processed ices and gases. The giant impact model, however, suggests a wild and chaotic early system where colossal collisions between giant planets were not rare events but a fundamental part of how planetary systems are assembled. Data from the Juno mission, which has provided our most precise measurements of Jupiter's gravity field and atmospheric composition, is still being analyzed to weigh the evidence for each of these ideas. Each measurement of a noble gas abundance or a precise oxygen-to-carbon ratio brings us closer to understanding whether Jupiter's formation was a story of quiet icy accumulation or a violent cosmic crash, a mystery written in the subtle deficiencies of elements that most of us have never heard of, but which hold the key to the planet's astonishing origin story. But our journey through the Jovian system doesn't end at the planet itself, because one of its moons holds a secret that could redefine our search for life beyond Earth. Looming in the frozen darkness, the moon Europa is a world of gleaming ice, crisscrossed by a dizzying web of rust-colored cracks and fissures. For decades, scientists have been virtually certain that a vast, global ocean of liquid water hides beneath its icy crust, an abyss containing perhaps twice the volume of all Earth's oceans combined. This belief was based on theoretical models of tidal heating, the idea that Jupiter's immense gravitational pull flexes and stresses Europa's interior, generating enough warmth to keep that subsurface water in a liquid state. The evidence, however, was always indirect, inferred from the moon's smooth surface and magnetic field interactions. That all changed when the Hubble Space Telescope and later other observatories witnessed something astonishing: gigantic plumes of water vapor sporadically erupting from Europa's south polar region and shooting dozens of miles into space. Here at last was the smoking gun, direct samples of the hidden ocean being offered up to us for study. The existence of these plumes is thrilling, but their behavior is what creates a profound and tantalizing mystery. They are not a constant, predictable feature like the geysers on Saturn's moon Enceladus. Instead, they are frustratingly intermittent, flickering on and off without any obvious pattern. Some observations catch magnificent, towering eruptions, while others, looking at the exact same region, find nothing but silent, frozen stillness. This irregularity throws a major wrench into our understanding of the forces that drive them. If the primary engine is tidal heating from Jupiter's gravity, that force is relentless and constant. The gravitational pull Jupiter exerts on Europa doesn't suddenly switch off. It's a permanent, rhythmic flexing. So why would the plumes, which are a direct product of that internal heating, be so unpredictable? It suggests that the process is far more complex than simple conduction of heat melting the ice from below. Scientists are now exploring the possibility that the plumbing system within Europa's ice shell is incredibly intricate. The tidal forces may not just generate a steady warmth, they could be creating pockets of stress and friction at specific points within the ice. Imagine taking a flexible plastic ruler and bending it back and forth repeatedly. The point of maximum stress will get hot. Now imagine that happening on a moon-wide scale. This friction could create isolated reservoirs of slushy ice or even liquid water trapped within the shell itself, far above the main ocean. These pockets would be under tremendous pressure. A small shift in the ice, a crack propagating from a moonquake, a change in the tidal stress at a particular point in Europa's slightly eccentric orbit, could be enough to destabilize one of these pressurized pockets, causing it to burst through the surface in a brilliant, short-lived plume. Once the pressure is released, the vent could seal itself with fresh ice, going dormant for months or years until the internal pressures build up once more. This would perfectly explain the sporadic and localized nature of the eruptions. Another compelling theory looks not to the ice but to the ocean floor. It's possible that Europa's hidden seafloor is volcanically active, heated by the same tidal forces that flex the Moon's core. If hydrothermal vents exist on the ocean bottom, much like the black smokers found on Earth's seafloor, they could be periodically releasing immense bursts of heat and gases. These sudden injections of thermal energy could rapidly melt the base of the ice shell directly above them, creating a temporary and powerful updraft that forces water all the way to the surface. The plume would then last only as long as that specific volcanic episode, accounting for the transient sightings. This would mean the plumes are not just a window into Europa's ocean, but a direct signal from its potentially active seafloor, a place that could be teeming with the chemical energy necessary to support life. The maddening unpredictability of these plumes presents both an immense challenge and a fantastic opportunity for future missions. NASA's upcoming Europa Clipper mission is specifically designed to conduct multiple flybys of the Moon, and a primary goal is to catch these plumes in the act. By flying through the faint cloud of particles, its instruments could directly analyze the composition of the ejected water, searching for complex organic molecules or other biosignatures that would tell us if the ocean has the right ingredients for life. The irregular nature of the eruptions, however, turns this into a game of cosmic chance. It requires being in the right place at the exact right time, hoping that Europa decides to reveal its secrets during a fleeting 45-minute flyby. Understanding the trigger mechanism isn't just an academic exercise, it's the key to unlocking the greatest secret this ice-covered world holds. Yet the most astonishing aspect of this million-ampere river of charged particles isn't its sheer power, but its seemingly impossible stability. This is not a chaotic, sputtering arc of electricity. It's a sustained and remarkably steady current, a constant flow of energy that has been maintained for the billions of years of the system's existence. This persistence is the true mystery. In any earthly electrical system, such a colossal current would generate immense heat through resistance, causing wires to melt and circuits to fail almost instantly. The space between Io and Jupiter is not a perfect vacuum. It's filled with a tenuous but present plasma that should offer some resistance. Furthermore, the system is subject to wild fluctuations. Io's volcanic activity is not constant. The density of its plasma torus varies, and Jupiter's own magnetic field is lopsided and wobbling. Given this incredibly dynamic and hostile environment, the circuit should be highly unstable, flickering on and off or shorting out entirely. The fact that it doesn't suggest the existence of a hidden, self-regulating feedback mechanism, a natural governor that we have yet to fully comprehend. This stability likely arises from a complex and beautiful balance between the circuit's power source and its load. The power source is Jupiter's magnetic field, an almost infinitely powerful generator driven by the planet's rapid rotation. The load is the ionosphere of Jupiter itself, the layer of charged particles in its upper atmosphere where the current finally discharges. Theorists propose that this system naturally self-regulates. If the current tries to increase, perhaps due to a surge of volcanic material from Io, the increased flow of electrons would cause more intense heating and ionization in Jupiter's ionospheric polar regions. This would make the ionosphere more electrically conductive, effectively lowering the resistance of the entire circuit and making it easier for the current to flow, preventing a dangerous power surge. Conversely, if the current wanes, the ionosphere would cool and become less conductive, increasing resistance and helping to maintain the current's flow. It's an exquisite natural balancing act, an automatic cosmic thermostat that keeps this incredible energy flow running smoothly against all odds. The consequences of this stable, high-power circuit extend far beyond the silent transmission of energy through space. They physically sculpt both worlds involved. For Io, the effects are written across its very surface in yellow and orange hues. The electrical current doesn't just flow passively, it actually strips material away from the moon. As electrons and ions from the flux tube bombard Io's surface and thin volcanic atmosphere, they sputter atoms directly off into space. This process contributes significantly to the replenishment of the Io plasma torus itself, creating a feedback loop where the circuit helps to sustain the very reservoir of fuel that powers it. This constant erosion is a key reason why Io, despite being the most volcanically active body in the solar system, lacks the large volcanic mountains we might expect. The moon is essentially being sandblasted on a planetary scale, its surface continuously weathered and leveled by this relentless electrical sanding. For Jupiter, the effects are even more dramatic and visible. This current is the primary power source for the most magnificent auroras in the solar system. Where the million-ampere electron beam finally smashes into the planet's upper atmosphere near the poles, it unleashes a torrent of energy that excites hydrogen molecules, causing them to glow in brilliant, shifting curtains of ultraviolet light. These auroras are not just driven by the solar wind like Earth's, they are predominantly powered from within by this moon-planet connection. The footprint of the Io flux tube is actually permanently etched onto Jupiter's polar aurora, visible as a bright, swirling spot that trails slightly behind the moon's orbital position. This creates the astonishing spectacle of a celestial tattoo, a direct and visible imprint of a moon's orbit on the face of its giant planet, a glowing signature of their electromagnetic embrace. This circuit demonstrates that planets and their moons are not just gravitationally bound. They can be wired together by invisible lines of magnetic force, engaging in a continuous, energetic dialogue that shapes their very evolution. After exploring the evidence for a hidden ocean on Europa, our journey through the Jovian system brings us to the most speculative and captivating question of all. Could life itself find a way not on one of its moons, but within the giant planet's own tumultuous atmosphere? The idea seems to defy all logic. Jupiter is a world of crushing pressures, blistering radiation, and violent winds, a seemingly hellish environment where nothing could possibly survive. Yet for decades, visionary scientists like Carl Sagan and Edwin Salpeter have dared to propose that life might not only exist there, but could actually flourish in a form so exotic it challenges our very definition of biology. Their hypothesis invites us to imagine a truly alien ecosystem, one that floats, drifts, and soars through the endless sky of a gas giant. The foundation of this incredible idea lies in identifying a potential niche, a place where the conditions are just stable enough and the ingredients just abundant enough to allow for the chemistry of life to begin. That niche they proposed is not on a surface because there is none, but within a specific layer of the atmosphere. As we descend from the cold, thin cloud tops, we pass through a region where the temperature and pressure become remarkably Earth-like. At a depth where the pressure is between 1 and 10 times that of Earth's surface and the temperature ranges from 30 to 150 degrees Fahrenheit, we find a sweet spot. Here, the environment is surprisingly clement, a vast global band of sky that could serve as a habitat for life that has never known the touch of solid ground. Within this aerial ocean, the key ingredients for life as we know it are all present, albeit in unfamiliar forms. There is abundant water, not in vast liquid seas, but as droplets within clouds. There are simple organic compounds like methane and ammonia, and plenty of energy sources. This energy isn't just from the weak, distant sun. It comes from within, in the form of Jupiter's own intense internal heat rising up to create powerful convection currents, and from lightning strikes that could provide the spark to jumpstart chemical reactions. The constant vertical churning of the atmosphere could even serve a vital purpose, cycling organisms between different chemical zones and preventing them from either sinking into the inferno below or rising into the frozen, irradiated void above. But what would such life look like? Sagan and Salpeter playfully theorized three distinct ecological roles for Jovian organisms, crafting a beautiful and bizarre food web in the sky. At the base would be the sinkers. These would be tiny, simple organisms, perhaps little more than self-replicating chemical soups enclosed in a membrane. Their existence would be a constant struggle against gravity, as they would slowly sink down into the hotter, deadlier depths. To survive, they would need to find a way to return to the habitable zone. This is where the floaters come in. These would be gigantic, balloon-like creatures, perhaps kilometers across, filled with lighter-than-air gases like hydrogen or helium produced by their own metabolism. They would drift blissfully in the comfortable atmospheric layer, harvesting nutrients from the air around them and maybe even consuming the sinkers that drift into their path. Finally, there would be the hunters, predators that would soar through the clouds, preying on the floaters in a dramatic aerial ballet that would be both terrifying and magnificent to witness. The most significant obstacle to this entire concept is the absence of a liquid water medium, which we consider essential for the biochemical reactions of life. How could metabolism or genetics function in a free-floating gaseous environment? This is where the hypothesis pushes the boundaries of known science. Life here might not use water as its solvent. Instead, it could rely on liquid ammonia or even hydrocarbons, which could remain liquid at the temperatures and pressures found in this atmospheric layer. Its genetic material might not be DNA or RNA, but some other completely alien information storing molecules stable in such an environment. These hypothetical organisms would be built from a fundamentally different chemistry, making them not just extraterrestrial but truly extraterrestrial. While this remains the most speculative of all Jupiter's mysteries, it serves a profound purpose. It forces us to expand our imagination and challenges our Earth-centric view of what life requires. In teaching us how life might arise on a world so utterly different from our own, we ultimately learn how to look for it everywhere. From its potentially smoldering, fuzzy heart to the impossible geometry of its polar cyclones, Jupiter is a world that continually defies our understanding and rewrites the rules of planetary science. We've traveled through its chaotic, lopsided magnetic field, witnessed its self-powered auroras pulsing with X-rays, and seen how it cooks its upper atmosphere with a mysterious energy source we are only beginning to fathom. We've watched its colossal storms rage for centuries and explored the hidden ocean on its moon, Europa, a place that might just hold the ingredients for life. Every layer of this gas giant, from the diamond rain in its depths to the faint, dusty rings sculpted by invisible magnetic hands, presents a puzzle that challenges our most fundamental assumptions about how planets form and behave. What makes this journey so profoundly exciting is not just the answers we might one day find, but the sheer scale of the questions that remain. Each mystery we've explored is a doorway into a different realm of extreme physics, a natural laboratory that operates under conditions we can never fully replicate on Earth. The story of Jupiter is still being written, with every spacecraft flyby and every new observation from telescopes here on Earth adding another piece to a puzzle that seems to grow more complex the more we learn. This isn't a world we will ever fully figure out. It is a constant reminder that the universe is a place of infinite wonder, always ready to surprise us with something new and utterly astonishing. Now we want to hear from you. After this deep dive into the 25 most mind-boggling mysteries of Jupiter, which one captured your imagination the most? Is it the enduring fury of the great red spot, the haunting possibility of life in its clouds, or the bizarre geometric perfection of its polar storms? Let us know your favorite in the